Hello all. Today we'll be learning the next concept of the substitution technique, that is the Hill cipher. In the previous lectures, we have learned the different substitution ciphers, wherein we have seen the Caesar cipher is the basic cipher which helps to convert your plain text into the ciphertext, wherein we substitute the alphabets, the single alphabets into its corresponding ciphertext letter. Then we've seen the other techniques wherein we are converting the more than one letters of your plain text into the ciphertext, which improves the security of your plain text. So here also in this Hill cipher, we'll be seeing how it again improves the security of your data, how it again improves the security of your plain text before its transmission over the network. Let's begin with the lesson. Hill cipher, it is considered as the polygraphic substitution cipher because it is based on the linear algebra. You might have studied the concept of the linear algebra in your mathematics in the first year, and linear algebra because it includes the matrix calculation also. This particular Hill cipher was invented by the scientist named as Lester S. Hill in the year 1929. It was considered as the first polygraphic cipher in which it was practically operated that more than 3 symbols can be converted into the ciphertext at once. In this cipher index, the Caesar cipher is used. The index, the basic concept of the Caesar cipher is used here. Here, the plain text is used in the column matrix in the form of the two in a single column, and the key will be given in the form of the matrix. Generally, in exams, if the Hill cipher question comes, then for the conversion of plain text into the ciphertext, the key is given. Either it will be in the form of 2 by 2 matrix, or it will be in the form of 3 by 3 matrix. Depending upon the type of the key, you will have to then make the pair of your plain text into the size of your key. That means if the key is of 2 by 2 matrix, then you will have to create the pair of 2 letters. If the key is of 3 by 3 matrix, then you'll have to create a pair of 3 letters of your plain text. So these are some of the key points of the Hill cipher, wherein each letter is represented by a number modulo 26, because we have total 26 alphabets. Here we have to follow the simple scheme wherein we will be then assigning each alphabet a number starting with 0, and as we have 26 total number of characters, so we'll be beginning by assigning 0 to A, 1 to B, and so on till we assign 25 to Z. This is not an essential feature, but generally for the calculation purpose, for the easiest conversion of your alphabets into numbers, this scheme is used. And to convert and plain text into the ciphertext, that is to encrypt a message, each block of n letter is multiplied by an invertible matrix against the modulo 26. And on the opposite, to convert the ciphertext into the plain text, that is to decrypt your message, each block is then multiplied by the inverse of the key matrix, which is used during the encryption process. That means whatever the key matrix we are using for the encryption process, we just have to find the inverse of that key matrix to perform the decryption process. In today's mathematical, or we can say the scientific calculators, the inverse of a matrix can be easily found without any hassle, but those who want to know the concept of finding the inverse of the matrix, the key matrix, I'll be giving you another lecture on that at the end of this module. So the matrix used for encryption is the cipher key here, and it should be chosen randomly from the set of invertible and n into n matrices, that is of modulo 26. This way we will be then arranging the alphabets, and then we will be assigning the numbers to each and every alphabet starting from 0 to 25. just begin with the example having the plain text network. When we have to convert this word network into the ciphertext, what we have to do is we just have to make a pair of two letters, that is an ETWORKX. We can see here that every alphabet is being assigned by its corresponding number. That is, N is being given as 13, E as 4, T as 19, W as 22, O as 14, R as 17, and K as 10. You can just verify these numbers from the table which is given here in this slide. Here we have a key of size 2 by 2, and therefore we use a pair of plain text having the letters 2 in it. The key is here, the key is 2313. Now let's begin with the calculations. We have the encryption formula. C is equals to KP mod of 26. K is nothing but the key matrix. P is your alphabets from the plain text, which we will be then writing in the form of a column. So if we substitute the values in the formulas for the encryption, we get 2313 as the key matrix multiplied by the column matrix of the alphabets from your plain text, that is a pair of alphabets 13, 4, and we have to multiply it with mod 26. If we perform these mathematical calculations, we get the answer as 38 mod 26, which gives you the numerical value 12. And if you compare the numerical value in your table, it will give you the alphabet as M, the corresponding alphabet M. Again, 25 mod 26 will give you 25, and which will give you the corresponding alphabet as Z. So here, after calculation for the encryption using the formula of encryption, we get the ciphertext for the plain text pair NE as MZ. In the similar manner, we can find the ciphertext for the other pairs of the plain text. That is, we have the other pair as TW, for which we can get the ciphertext as AH. For the pair of OR, we can get the ciphertext BN. And for the last pair, that is KX, we can get the ciphertext of LB. Thus, by using the encryption formula C is equals to KP mod 26, we can convert your plain text into the ciphertext, that is MZ, AH, BN, LB. Now you can see that this ciphertext doesn't have any meaning. It doesn't form any word which has any meaningful sentence or which can be used in any meaningful sentence. Now let's start with the decryption process. Here the formula for decryption is P K inverse C mod of 26. As I told you, we will have to first find the inverse of the key matrix which we have used for the encryption, and the first ciphertext pair will be MZ. So the after calculations, if we get the value of K inverse as 125, 17, 18, and for the first pair of cipher, that is MZ, which we have calculated for NE, we have values as 12, 25, corresponding to the alphabets M and Z. So we'll be writing those values in the form of the column and then mod of 26 according to the formula. And if we compute these values, we'll be getting the value as 637 mod 26 and 654 mod 26. If we again calculate these values, we get the last column as 13, 13, 4. That is, if we compare these numerical values with the alphabets, you'll get the value 13 corresponding to N and 4 corresponding to E. That means after decryption, the first ciphertext pair which we had as MZ has been now converted into its corresponding plain text having the pair of letters as NE. Thus we can get out our plain text back after the decryption process. And if we perform the decryption for in the same manner for the other pairs of the cipher, we will be then able to get our plain text letter back. That is, for AH, if we do the same decryption process, we'll be getting the plain text TW. For BN, we'll be getting the plain text OR. For LB, we'll be getting our plain text back as network, that KX. That means after the decryption process, the ciphertext has been converted into its original text, that is the plain text network. So in this way, we can use the Hill cipher for increasing the security of your data by converting more than 3 symbols at a one time. And here we have considered the pair size, the key pair size as 2 by 2. That's why we have created the pair of 2 letters. If we have the key size 3 by 3, we can make it as 3 letters also. So in that case, we will then be converting 3 letters at a time into its ciphertext letters. So in this way, it increases the security, it improves the security of your data before the transmission. Hope you might have got the concept of the Hill cipher. Thank you.